This
just
conference will now be
repost
recorded.
that question again on your chat, okay? But what I will do is I will be taking these questions in between if you put it over chat, and after that, after 45 minutes, I will stop and I will just ask each one of you to start asking questions, okay? So that way everyone gonna understand each thing that I'm gonna talk today. Cool? Yeah. So thank you. So let's start with the regression. So what is regression and why we need to do regression? And the very first thing when we talk about these days is like we're talking about data science, you're talking about machine learning, artificial intelligence, and again we're talking about deep learning. Okay, so all of these things looks quite good, but again, you cannot underestimate the importance of regression even in this world. And regression is more than, I think it's there for more than 200 years. Okay, and maybe bigger. Yes, the session has started, Ankit. Please check your connection, Ankit, because I talked to other people. Each one of them was able to hear. So it's quite an old thing, which still is very relevant in today's age. And the reason is because if you do any kind of advance, if you use any kind of advanced algorithm in today, what problem you will face is that you will not be able to understand the impact of each variable, okay, each driver. Okay, so what happens is, let's say if I really want to understand that will there be rain tomorrow, okay, and for to predict that particular thing, I also need to understand what are different factors that are there which are important for a rain prediction. Okay, it's about soil moisture, is it about cloud, it's about the type of cloud, color of the cloud, size of the cloud. Okay, there can be numerous amount of such variables which you can actually put into your equation. And when you kind of put each one of these into your equation, then you really want to understand that what is the importance of the size for predicting rain, what is the importance of the color for predicting rain. Okay, so if these are the things, then you actually always want to use regression, because regression always helps you in understanding everything at a very basic level. And the second important thing about regression is that when you try and present it to business users, okay, because what happens is most of the time, because we have gone through so much of detailed studies about deep learning, neural networks, all these different stuffs. But what happens is at times, again, these things are kind of black box. You also don't know what's happening inside it. Okay, and when you try and go and present it to any business user, okay, and maybe just think of, you want to present any result to your mom or grandmother, okay, in that case, what would you prefer? Would you prefer to tell her something about deep learning, or would you prefer to tell her something about regression? Like, my vote is about regression, because you can, after today's call, I'm quite hopeful that you will be you will be able to easily explain regression to you, any like to any senior in your home. Okay, so let's start with the thought. Let's start with the regression. So what are the basic things about regression? I will just, I'm going to cover theory quite quickly, and we'll be doing more hands. I will be writing more things today. Okay, so just watch for that. So what is modeling? It is based on regression analysis. Yes, we all know. There's nothing new about it. It can be used for the following two distincts. Okay, so what happens, okay, in a regression? So let's try and understand that first. Cool. So what happens in a regression is, let's say you have a variable y. Okay, and I'm sure we all have gone through our higher secondary mathematics. Okay, so what we used to do, we used to, I'm sure you would have learned this equation, y equal to a x plus b. Okay, I'm sure this equation should be able to tell you, it's not unfamiliar to you. Okay, so what does it mean? Let's try and understand it. So here in regression terminology, what happens is y is actually your dependent variable and x is your independent variable. Yeah, this is the equation of a straight line. But let's say if I just change this to another equation which says y equal to ax square plus b. Okay, and if I kind of run this, can I say this is a part of regression, linear regression? No. Okay. No. Parabola. Okay. No. Correct. So let's say if I kind of just plot my value of my x. Okay, correct. So yeah, that's what we're going to talk. So why we talk about linear regression? The meaning of linear regression is that the relationship has to be linear in nature. Okay, and so if you look at this particular equation, this relationship is linear. Okay, with all these independent variables, it's just plus. Okay, you can have more variables here, and they're all kind of linear in nature. You're not multiplying them. Okay, the other relationship can be a x1 into b x2 into c x3. Okay, this is not a linear relationship. Okay, this is a linear relationship where you're saying y equal to a x1 plus b x2 plus c x3 plus d. Let's say this is your equation. This is known as linear equation. Now what we are saying is, and this is also known as multiple regression. This is an example of multiple regression. If I had only this equation, ex1 plus b, then this is an example of simple linear regression because you have only one variable based on which you are trying to predict your dependent variable. Yes, so whenever you have more than one independent variable, it is known as multiple regression. Now we also talked about this another thing, which is your y equal to ax square plus b. Okay, so some of you are saying this is not a linear regression, correct? But let's say if I say x square is equal to x dash. And now if I say y equal to a x dash plus b, can I say now this is, so can I say this as a linear example of a simple linear regression? Correct? Okay, so you're saying that yes, this looks to you like a simple linear regression, correct? So what about this? Can I say this is also an example of simple linear regression? Okay, you're still saying no. No, I think no. So this is okay. Let's say in this particular example, this is your equation. What if I say xt is actually equal to x1 square? Okay, we were saying that this is again an example of simple linear regression. But the moment we do this, yeah, this is so the question basically the answer is all of them are linear in nature. Okay, you're not talking about individual curve for each of these variable. Okay, so if you plot this x square, just this x square, obviously this will gonna come something like this. But what you're trying is you are identifying the relationship between y and this, and irrespective of the form of x, it can be x cube, it can be x cube, it can be square root of x. Okay, multiply with some coefficient, it can be anything. But based on that whole thing, you're just identifying that relationship. Okay, this is what you're trying to identify. So this is still an example of linear relationship. So if somebody asks you, gives all these different forms, you will always be you should confidently say that as long as you have like these pluses in between different independent variables, it always shows you a simple it always represents you an example of regression. But then y is varying in real value range for x. Yeah, so I can also change my y, correct? I can say y actually is equal to y dash square. Okay, it can take any transformation. So what happens is, okay, sure, cool. So what we are saying is y equal to ax1 plus c. Okay, this is our equation one, and we are at the very first point we are saying this looks like a linear regression, simple linear regression, correct? But what if I say y is actually equal to y dash square? Okay, or y is equal to log of y, log of z. Okay, something like this can happen. Okay, a lot many times when you try and run these regressions, it always that you have to transform your variables into different formats. It can be that y is actually equal to y dash cube, anything like that. So what you're doing is you're just replacing it with another variable and finally you're representing it in this particular way. Okay, so as long as, so what linearity means is, this is important in the linearity. As long as you'll keep seeing these simple additions, it means your whole relationship is linear in nature. Okay, so what does it mean? What does that linearity means? Okay, this is your variable one, irrespective of any value. If you add something on top of this, if so, you, let's say something like this kind of thing is happening. If you add something c to this, your line will reach to this another. Okay, this is your value of c, let's say, and this is your value of ax1. So you have just added c to it. Now this is your y equal to ax plus c, ax dash plus c, correct? So this is a linearity. This is the meaning of the linearity in simple linear regression. Okay, did you understand this? Cool, perfect. So now you know what is a simple linear regression. Let's try and go a bit deeper. And for that, let's say you have a very basic example. Let's say you have mouse size and weight. Okay, so you have these little mouses in our houses, and you have gathered data. Let's say you have hundreds of such mouses somewhere, and you have somehow gathered their data. Okay, so you have the, okay, and you have data like their sizes and their weights. And what you want to predict is based on, you want to predict their weight. I will just denote it as by w, and this is by size. Okay, you just want to predict their weight based on their size. Okay, so let's say this is what you want to predict. So how you going to do this? So obviously, first of all, you need to gather data. So for, let's say you have 100 different mouses. So first mouse, you will have his size, you will have his weight. Okay, and what you will do is basically you will just create a very basic table like this. Okay, you will just create this table, and where you will have all different values. Okay, and let's say you have these 100 different values in front of you. After this, what next will you do? The very first thing is, like, we all have quite curious mind. The very first thing that we need to do is like how these weight and size are correlated. So intuitively, the feeling is, if any mouse is bigger in size, its weight should be more, correct? The bigger the size of a mouse, how higher the weight of a mouse is. That's why it's very intuitive. Yeah, so in simple linear regression, just to answer Saurabh's question, we always predict real values, not 0 1 probability range. Yeah, so in simple linear regression, our y has to be continuous. The dependent variable, this y equal to ax plus b, this always has to be continuous. Okay, meaning it should not be having any discrete value. It should be just like when we're talking about weight. Okay, the weight is always a continuous number. Yeah, the 0 to 1 is actually for logistics, and there are a lot many other things you can do. It's not just for logistics, you can also run a more advanced algorithm on top of it. Can we predict categorical variable in linear regression? Yes, x can be a categorical variable too. So you can just say, you can also add, let's say, based on the gender of mouse. Okay, so then it's based on the sizes plus gender. So you can also add, yes, linear regression is a classification problem. Yeah, you are correct, Kanjal. But just wait for a minute, because I'm sure you guys would be reading a lot of literature around this. But in today's class, what I want to teach you is basically a more basic concept, a very fundamental concept from which we really want to understand very basic parameters like r square. How do we calculate it, and why it is that important? Okay, so just wait for a couple of more minutes and then start asking more questions to me. Okay. So what is the difference between regression and classification? So regression is one of the algorithm that falls under the classification. Okay, you're classifying it based on basically the y, which is, and by using the regression method. So it's one of the method that falls under the classification. Okay, so let's try. So what is our problem? So our problem is, let's say we wanted to identify the uh, weight of the mouse based on the sizes. The very first thing what you do is you try and plot a correlation curve. Okay, so let's say here you have your size, and here he have mouse weight. Sorry, weight. Then what next? You will be putting some dots. Okay, and then you will be identifying some correlation. Okay, so this is the very first thing. The next thing is, now you want to, and so let's say the correlation comes out to be 0.7. Okay, this is your correlation coefficient. Now what next? Let's say you also have this gender. Okay, let's say some other variable, continuous variable, age. Okay, instead of that, how old is that mouse? You again plot its weight versus its age, and again you have those some numbers. You again get to know that the correlation is 0.5 this time. Okay, so now the very first question that comes is, just based on the correlation, would you be able to say that how much impact of size is, what is the impact of size in comparison to weight? So if you want to compare your size and weight age all together. Okay, so you have two variables, size and age, based on which you are trying to predict weight. If you want to compare the impact of size with respect to age, then how much is it? Okay, so you want to calculate that relative matrix. So will you be able to use this correlation coefficients? The answer is no. Even though you know that the size and weight, they are both uh, positively correlated with the weight, both the size and the age, they are both positively correlated with the weight. But if you want to understand the relative impact of size with respect to age, you still won't be able to do it. And that's when the linear regression comes to our help. So let's try and take an example. How do we calculate, try and get basically linear regression? So let's say you have this whole, you have already plotted these different points, and let me just use this color. No, let's use this color. So let's say this is one point that you have, this is another point that you have, this is this point you have, and this is this point and this point. Okay, and this is your weight. Sorry, this is your size, and this is your weight. Okay, so what happens is, right at the start, let's say, what is the very basic thing that you'll be doing? So if I ask you, on an average, what is the size? The very first thing we all will be doing is calculating a mean. Okay, correct? And what we can do is we can also calculate the mean of weight. So we can calculate mean of size. We can also calculate mean of weight. Okay, and then based on these we can just derive a linear relationship and do all kinds of calculation in your mind. This is a very basic thing. So if I ask you, what is the average average temperature last year in Kolkata, okay, let's say that's one example. So what you will do is you will just look at the whole temperature thing, all records for the last 365 days, you will take a mean and you just talk about that. So now what happens is, if you in a regression context, if you really need to understand this particular thing, okay, so what is a very basic thing that you really want to predict? The basic thing for weight, how will you predict a weight? Okay, mean is the very simplest thing for any prediction of weight. So what you will do is, if I ask you that, let's say if your rain is your dependent variable, and you want to use the simplest or the simplest algorithm. So linear regression is still an advanced algorithm. The purest and the simplest form of prediction is your using your mean. So what you will do is, If I ask you what is the average, what is the rain, what is the temperature that you expect tomorrow, you will just take an average and tell me that this is the temperature that you can expect tomorrow. Obviously, there will be, it might be that same temperature tomorrow. It might vary a lot. Okay, if it's vary a lot, that means there's a lot of error in your prediction. So what happens is, in this case, let's say this is the average weight that you have of all these mouses. Okay, so this is a line of the average weight. Now what you do is, this is the average line. You try and this is your actual weight of the mouse. So you identify this height. Okay, you calculate this number, you again calculate this number, you calculate this number, you calculate this number, you also calculate this number. Okay, and this is actually known as your variance of mean. Okay, so you calculate variance of means from here. Okay, and when you calculate this variance of means, what happens is, basically whenever we talk about variance, it's again a kind of average, but it's average of squares. So let's say if you just take the average of this right now, what happens is, this will be in this error. This is, let's say if I say this is, difference is an error, this is a positive, this is a negative, this is a positive, this is a negative, this is again a positive error. So some of these will be cancelled out, but an error is an error. Okay, irrespective of its being positive or negative, so we should be adding all of them up. So in that case, what do we do is, we basically take square of these two. The moment we take square of these errors and then start adding them, so in that case what happens is, we are not able to reduce this, uh, neglect this negative part. Okay, we are adding it up on top of what errors you already have, so we are making it again linear in that terms. So variance, we calculate the variance, and this is basically sum of squared errors, okay, divided by n, total number of points that we have. So this is how we calculate the variance of mean. After that, what happens is, let's say you do a prediction. You and also identify equation like this: y equal to ax plus b. You have got this equation. Now you start predicting. Okay. So in that prediction, let's say, let me just mark it with a different color. Let's say this is a line that you have got. Okay, now in this particular case, again what you have is, basically you have a point here. Okay, so you have your point here, this much you are able to predict. Okay, and this is basically you are not able to predict. So this is an error which you are able to predict, because let's say if you've done this prediction, you already know your original point, and you know this is where this point going to lie in your equation. So this much point you're able to predict, but this much is you are still not able to predict. So this is known as unexplained error, unexplained part of your prediction. Okay, and this much you are able to predict with a lot of accuracy. The same thing gonna happen for every point that you have. So, and this is also known as your fit curve. So whenever you predict anything, okay, and you kind of put these curves, they are all known as fitting curve. So now what happens is, you also calculate the variance of fit. Okay, and variance of fit will all again will be equal to sum of sum of squared error, but for fitting line. Okay, and divide by n, meaning now instead of taking this whole thing, you're only taking this much, this much value. Here you will take this much value, here you will take this much value. Okay, only this much value you will take to calculate your variance of fit. Okay, so now we have these two important things. After that, the next thing is your r square. So what is your r square? Your r square is 1 minus your variance of fit divided by variance of mean. Okay, this is how you calculate your r square, and this is very very important, because if you know it using this basic fundamental, then you can crack any kind of problem in future. Okay, this is very very important. Variance fit exponentially once again, exponential. Okay, okay, let me try and create another diagram. Cool. So I hope you understand what is the meaning of variance, correct? And why we need variance. So we all know what is the average. If you have 10 numbers, you all can calculate an average, correct? Now why we need to talk about variance? Variance is also an average, okay, but it's an average of squared, something being squared. And why we need to do squaring? Because if the error can be positive and negative, and if we just calculate the normal mean, so in that case what's going to happen is my positive negative is going to cancel out some amount, which is not good. So what I do is I square every error and then add them up and then I take average. Okay, this is what you, in very very raw terms, variance is all about, okay, for a particular variable. Now, thing is, let's say if here again we have these points, okay, and this is our prediction line, correct? This is what we have predicted, and we also have our average line. So our average would be something like this. Let's see. Okay, this is your mean of this y. This is your x. Yes, so you can take absolute value also, but the concept of variance is being defined using squares. And there's one more thing. So when you square, okay, so let's say so there's that's a very good question, Saket, that why not just the absolute value. So what happens in squaring? So when you square an error, okay, let's say an error can be more than one, an error can be less than one also, okay. The moment you square your error, okay, if its value is more than one, what's going to happen, it will multiply, it will have bigger impact, versus if you have error less than one and then you square, the value of the error will reduce, correct? So in that case what happens is whenever you're using this squaring, okay, squaring thing, it's gonna give more weight to the errors which are bigger in nature, okay. So you understand the weighing average concept. So if you use square concept, one of the basic thing it does, it gives more weight to bigger errors and it gives less weight to small errors. Just for example, let's say you have error 1, okay, let's say this is your you have error 1 is zero point 0.5 and your error 2 is 5, okay. Now if you square them, so this is your 0.25, so it's reduced, the value is has been reduced, but if you square this, it has increased 25, okay. So that means if you do a absolute error calculation, in that case each one of will have equal weightage, but in this particular case the weightage terms is more biased towards the higher number, and that's why we want to do this most of the time, and that's why we square them up. Cool. So now let's come back to our example. So this is what we have. What we're going to do is, this is what we have predicted, okay, and this is our average value. Anyway, this is our total error. Out of this total error, this much error we are able to predict, and this much is unexplained. We can't predict this much error, okay. And that's why whenever you try and see r square value coming, it never comes 100%, okay. It never comes 100%, it always comes to 70, 60, 50%, okay. That is the reason. The moment, let's say, if your graph, this prediction also aligns with the mean, okay, then what's going to happen is, so let's say what was the formula for r square? 1 minus variance of fit upon variance of mean. This is a formula. So what happens is, the moment you have your fit value, basically, let's say if at some time your curve also becomes something like this, okay, this red dotted line, which is basically kind of overlaying on top of this blue line, then what happens is your this distance, which is you're able to explain, become equal to this whole thing, and your r square will go to 1, will take a value of 1. That means you will be able to predict each and everything of your curve, okay, of your data, which normally is not true, and we don't want to do that also. Okay, that is very very important thing. So this is how you try and break your error. Your error has two parts. It has one unexplained part, it has one explained part. Whenever you're predicting using any equation, you're able to explain that particular thing using r square. Okay, so r square is basically how much variance you are able to explain, and the more variables you add, the higher the number of variance you will be able to explain. Okay, so just think of this thing in 3D format. So you will be having something like this. Okay, so initially you will, let's say this is your age, this is your size, and this is your weight, and you will try and predict something first here in between and then with something here. So just think of, it's quite difficult to draw it here, but like if you have some okay, so you have so it's a 3D thing. So you have to just visualize this in a better way. Cool. So now the next thing is you understand the concept of r square. Then what are the parameters we need to consider? R square equal to 0 question. I think if that's a question, if r square is equal to 0, so that means you are not able to predict anything. Okay, so just think of like if this is a mean, your prediction is something like this whole vertical line. Okay, this is your prediction. If rs is 0, that none of you are not able to predict it at even a like point 0.1 kind of variance in your system. Okay, here you should not be using that particular model. Cool. Now but let's say if you have only two variables, okay, only two data points. So in that case, what's going to happen is you can have your line like this. You can have your line like, okay, you can always have one way of identifying. R square can be negative. No, R square can't be negative. Okay, and you can understand why it can't be negative. You're saying R square is equal to 1 minus, okay, variance upon variance. Okay, here you have fit and here you have mean. Okay, and these variances, they're also squares. Okay, and this is always be bigger than this. Practically it seems can be negative, theoretically not. I don't know how are you able to see it as negative. It cannot be negative even like being it theoretical practical, but it can't be. Just think of, you have variance is always sum of square. Okay, so your variance of fit will always be less than equal to this. Okay, so this your bottom denominator is actually the upper bound of your variance of fit. Okay, sorry, Rohan, I'm not get what did ESS and RSS. I'm not sure what you mean by that, unless you kind of put that in full form. But just give me another 10 minutes and let me try and finish this concept of basically this thing on regression, and then we'll take all of your questions. Okay, cool. So now the thing is, let's say you have these multiple data points. Okay, you can have a line like this. This is one of the option in terms of your prediction. You can also have a line like this, which is again another prediction. You can also say this is your line. Okay, so how will you come to a conclusion that out of these three lines, which one is your best fit? Well, L1, L2, and L3. Okay, so how will you come to the conclusion which one of this is your best fit model? Any thoughts? Yeah, correct. So minimum residual, or you can say you will try and calculate the r square, and whichever line gives you a higher r square, that line you will try and choose. Okay, now another thing is, so let's say if you have only 2 points, point 1 and point 2, you can always say that irrespective of anything, there is only one line that can pass through 2 points. If you have 3 points and you have, let's say, a plane, okay, you have two variables, you can always again only create only one single plane out of those 3 points. So what happens is here, how will you say that is it significant or not? Because you're connecting just 2 points. And for that, what happens is basically you try and take help from, well, P. You try and, if you, the moment you start talking about that, let's say you have got a R square of zero point 0.8 or zero point 0.7, how do you know this is good or this will be valid? Okay, so you try and start talking about its significance, and the moment you talk about significance, the value of P comes into picture. P is actually the element of surprise. Okay, I'm sure you guys would have seen your periodic table. You would have read about periodic table in yeah, around 8 to 9 to 10th. I'm not sure about the class now, but you would have gone through the periodic table where the P means phosphorus. But in the world of statistics, the P means the element of surprise. Okay, and the higher the value of P, lower the value of surprise. So you generally want your value of P to be max by 0.05, okay, or 5%. If it's less than that, that means there's a very, very big surprise that's there for you, and you should actually would be considering it. That means your R square value is very, very significant. So that's how you kind of relate your P values to R square. Okay, after this, now the next important thing is our assumptions. Okay, so let me just go through a couple of assumptions. And when we're saying this is also known as OLS, ordinary least square method. Okay, you can also use the gradient descent method, but this kind of optimization, okay, where you're calculating the residuals, you're identifying errors, then calculating residuals, okay, then calculating R square, and then basically identifying where you're getting R square or minimum sum of squared error. This kind of way is known as ordinary least square. Okay, so now let's go to our back to our presentation. So at least from the concept point of view, we understand what is the regression and how to do it. Now let's try and think that how where all we can use it in terms of its practical application. And you can see that basically it can be used in various businesses. So it can be used in prediction of sales. Okay, and you can have a lot of different parameters like past sales of different goods across geographies. Okay, you also can take seasonality factors in it. So based on all these different factors, you can actually try and predict sales. We can also have basically various marketing mix models, where again based on the amount you spend in marketing, okay, basically on your online ads, Facebook, Google, TV, okay, based on those things you try and create some marketing mix models, which helps you in understanding that how much money that you have put is able to create how much impact on your final sales. This is what the marketing mix models are all about. You can also try and create claims forecasting models. Okay, so all these kind of things can be easily created using OLS regression, and that's why it's still being used a lot in most of the applications. Then what kind of models you can develop? You can create response models, conversion models, attribution models. Okay, so all these models are of basically have different names depending on the industry they belong to. Okay, and you can just think of basically it's kind of a toffee with a different wrapper. Okay, the toffee is still the same. It's everything like the behind all these models, the key concept is still your linear regression. Okay, and on top of that, then you can basically just run you can just give them a very different names. Cool. So now I think we've already gone through, this is the how we denote our linear regression. How to get, okay, very basic thing. And we so whenever we talk about this linear regression, we also want our variables to be normally distributed. Okay, this is what an example of normal distribution is. Okay, so this is a general explanation. We just tried to we just draw it. So you can see you have basically on x-axis your independent variables, on the y-axis you have your dependent variables, and then you kind of do this whole plotting of points, and then you try and put a line. You try and identify its r square, and wherever you in whichever line gives you the best possible r square, you try and select that. So this is what known as your linear regression, and you can see the example that we have just talked about at the start. Here all these forms would also be considered as a linear regression form, even though at an individual variable level they are not linear, okay, but at a overall level they are linear in relation. Now this is again one very important thing we need to understand. So a lot many times we are saying that, yeah, so let's say you kind of identified this, okay, Anscombe quartet, or what is the Anscombe quartet and why it is important. A lot many times what happens is we don't visualize our stuff and we rely a lot on basically our equation. So what happens is, let's say you have come across an equation and you think that that equation is going to represent everything. Okay, it's linear in nature, but not necessarily. And Anscombe quartet is actually one that very specific example which actually talks about this thing. So you can see there are four different graphs here. Okay, and each one of these graph has exactly same equation. Okay, and the r square. Correct. The equation and the r square, both things are exactly same. But if you kind of draw them, okay, you can see the plot is very different. So in this particular distribution, you're getting the same equation r square. This looks like a linear. This is a parabolic distribution. Okay. In this kind of distribution, also you are getting same equation and r square. But is it good to fit this kind of linear graph here? Answer is no. In this quartet, again, there is an outlier. Okay, there is an outlier in the system because of which it's impacting your prediction, and because of which you're still able to get the same linear equation output and r square. Okay, and you can again see this is another example where you again have basically the same equation, even though the visualization is not following the trend that you have. So that's where you always need to consider plotting whenever you kind of create your linear regression. So it's very important. Always try and plot and check what you have got from the as a output from the linear regression, because it might happen that your relationship is still not linear. Okay, you're predicting this linearity, not the linearity within the variable. Cool. So I think so this is what I have for today. I think linear regression is like quite an intense topic. We can just keep talking. I can just keep talking about it for hours and hours. But I think we only have now 15 minutes, so I'm gonna start answering your questions. And okay, so now let's make it full open. So I've got one question from Archana, and she's asking that can you explain the log form? Yeah, definitely. So why we take log? Okay, just try and understand that. So what happens is, let's say we have these numbers 1, 10, 100, 1000. Okay, and if we kind of plot them on a curve, what kind of curve do you expect? Will you expect a linear curve for these? No, correct. So they will not follow a linear trajectory. Okay, let's say I take log with the base 10. Okay, this will become 0. This will become 1. This will become 2. This will become 3. Okay, now if I plot this, can I say this is linear in nature? Okay, so that's where a lot many times when you take the log of any of the variable, it makes that variable linear in nature. Okay, because this is not linear in nature. The moment you plot it, you won't get linearity. Okay, basically I'm not sure. This is 1, 2, 3, and what is your? This is your 1. Okay, sorry, this is your 1. This is your, let's say, 10. So you're gonna get something like this. Okay, okay. Basically you're gonna get something like this. Okay, so just that whole thing you're able to transform it like this. Cool. uh, I've got one more question from, okay, so so then how can we understand we have to take log from before running the model? So whenever we run model, so I haven't had time to talk about all assumptions about linear regression. But the very first assumption that we have for linear regression is that each one of them, each of the variables should be linearly distributed. Okay, and should be normally distributed and should be linear in relationship. whenever you see something like this, okay, so you kind of plot each one of the independent variables independently, and you see how it's being distributed. If you don't find it linear in nature, in that case you try and use some transformation, and so log is one transformation. You can take square root, okay, you can take cube root, any kind of thing. You can also take inverse. So you try and plot all these different transformations, and then try and see if now you are able to make more linear, bring more linearity into the system or not. Cool. I think there's another question from Rohan. Rohan is asking, sir, if R and P values both are significant, then does it imply that it is a good fit? Cool. So R value can't be significant. You have to understand the significance of R value, okay? And to understand the significance of R value, you use the help of P value. So what you do is, if you have 5 6 variables based on which you try and predict your equation, so for each of those 5 variables you will get a p-value, and that p-value has to be less than 0.05. It is more than 0.05, that means this could have happened by chance, okay, and you don't want to take that chance. So you kind of remove those variables which has higher value of, which is higher than 0.05, okay, as a p-value. You remove those variables and then again rerun your equation, and once you have got the p-values for all the variables less than 0.05, at at that stage you say your regression is good, and obviously then you need to look at the r-square also. Okay, so Aniket is asking, yeah, Aniket, I'm coming to your point. And just before that, Kinjal is asking, for the quality of model, what should we check, the adjusted r-square or RMSE, root mean square error? Cool. So the very first thing, so it depends when you're talking about quality, how you want to define your quality. Whenever you want to, if you only have one single model, okay, it doesn't matter. You check R-square or RMSE. If okay, but if you, let's say, have multiple models, so in that case, you really want to see which one is giving you less error. So when you talk about R-square, in R-square, what happens is, you're talking about the effectiveness. It talks about the variance, how much variance you're able to explain. And in RMSE, it talks about, basically, it gives higher weightage to the errors which are higher, which is more than one, and it gives lower weightage to the error which is less than one. So both of these terms are very, very important. You can, depending on the context, you can, I would go with both. If you have, let's say, multiple different models, I will always try and expect to get higher R square and lower RMSE. Okay, and that's a constant juggle that you need to do whenever you want to select your models. Okay, now I'm going to take Aniket question. So can you explain variance fit? Okay, cool. So in the variance fit, what happens is, let's say you have this graph, okay, you have these points, and this is what your prediction is, okay, and this is what your mean is, okay. So what happens is, if this is your prediction, okay, this is what you're predicting. So here it's actually negative, but this is what the error you have predicted, okay. And if you, this is your mean line, and this is your fit line. This is what you have predicted as error, but actual error is like this, okay, from mean. This is the total mean error. So what you say is, when you try and calculate this, you will identify all these different scenarios. Here you will identify this. So let's say this is your E1, this is your E2. So when you try and calculate your variance of it, what you do is, you say E1 square plus E2 square divided by 2. So this is how you calculate your variance of it. Hmm? Cool. So Archana is asking, sir, during our R class, we were told that R square depends on location and data of that area. Okay, sorry Archana, I don't know what you mean by location and data of area. Definitely R is dependent on the data. That's definitely correct, but I don't know what you mean by location. Okay, Indu is asking when can we apply standardization and normalization? Okay, very good question. So whenever you talk about standardization and normalization, okay, just think of, let's say if you have an equation, something like this. Sorry. So we had this example of weight. Okay, weight is as a function of, we wanted to identify weight as a function of our size and age. Okay, and so let's say you get equation like this: weight equal to a plus b into size plus c into age. Okay, so in this example, let's say if you have just put the raw data and then you've got these coefficients. So what's going to happen is, now if you want to understand the impact of b and c, a size and age, okay, using these coefficients. But the problem is your size is, let's say, is in feet. Okay, this is a different unit compared to age. It's a number. So you will not be able to directly compare your coefficient b with coefficient c. Okay, and if you really want to know that is size is 30, like 2x more important than age or not, let's say that is the question that you want to answer. So if you have put the data in the raw format, in that case you will not be able to say inference, take any conclusion like this, because the units are different. So what you do is, you try and normalize your data. The moment you normalize your data, you make it unitless. Okay, so if you make your data unitless, and then I run the regression and then compare these different coefficients, okay, together, then obviously it makes more sense. Okay, because of that normality, or no, sorry, normalization in your data, you will be in a better position to compare that, yeah, the size is 2x more important than b by just comparing their coefficients. So this is why it's always recommended to do your normalization or standardization kind of thing in your data. So did that answer your question, Indu? Okay, so so I would say it's always, if it's about normalization, it's always good to use normalization. So let's say if you have different values, okay, in your equation, what normally going to happen is, you always have y equal to a plus b x1 plus c x2 plus d x3. Okay, and all these variables will be of different units. Okay, this can be in fit, this can be in centimeters. Okay, okay, and this can be, let's say, in, if this is temperature, degree centigrade. Okay, now if you want to compare the relative importance of bcd in respect of predicting the y, okay, you will not be able to do it if you haven't normalized your data. But had you been like doing the normalization, so in that particular case, you will be in a better position to understand the impact of bcd, basically your all these three variables, x2 x1 x2 x3, with respect to y. So that's why the normalization is becomes important exercise. But again, most of the time, I would say 95% of times, it's always good to do normalization. But at times you don't want to do it because you still want to preserve the originality of your variables and then try to understand its impact. So it again depends on the business context, but I still have seen, like, based on my experience, 90 to 95% of the times you try and normalize your data and then you run your regression. Cool. So guys, yeah, any more questions? No. Cool. So I think this is only the one of when to apply normalization is when to apply ST standardization. Okay, so there's very thin difference between normalization and standardization. Uh, it's like if you want to put everything between 0 to 1, okay, everything between 0 to 1, and that's when basically you try and do normalization. And I think let me just give you a very good example of show you a good example of normalization. So uh, have you ever tried Google Trends? Any one of you? Has any one of you tried Google Trends? Correct. So what do you see there? These people normalize their data, correct? Any thought why they normalize it? Let's say what's happening, IPL. This is should be the hottest topic. Okay, it can't be. Let's change it to India. Cool. Okay, IPL. Let's talk about CAA. Let's see how much people are talking about CAA. No, no interest over time. Oh, okay. Give me some. Let's say Coke or let's say Vivo. Cool. So what do you see here? So every data is actually being put between 0 to 1. Okay, this is a normalized data. Hmm? Let's say if I compare Vivo versus Oppo. So what do you see here? I also have Oppo and all of these values are being between 0 to 1. Okay, and I can see that Vivo has higher searches compared to Oppo. Okay, relatively. So even though I don't understand the exact exact numbers of searches for Oppo and Vivo, but still in a relative mode, I can still say the Vivo is more popular than Oppo. So this is a pure example of normalization. So normally you always try and do normalization for all of your variables so that you always try and understand your relative context. Now, when to apply standardization? So it's very close standardization, but the only thing with the standardization is at times you also kind of see negative values. Okay, so in that scenario, I will always try and go for normalization rather than standardization. But there's very thin difference between these two, so it's okay. The only reason for you for doing a standardization is basically, let's say if you want to calculate the standard deviation, and if you want okay so in this example, let's say if you want to calculate the standard deviation for this and you want to for your height, uh, okay, fit, and this is again for degree centigrade, you want to calculate the standard deviation for this. Now if you want to see which one of them is better, okay, so in that particular case, had you been done standardization of these variables and then you would have got that value, then it would have made more sense in terms of doing that comparison. Yes, it's more related to the creating a normal curve. Yes, cool. So thanks everyone. I think like is I can take one more question if you have, and I think we are already almost finished with our time. But thanks everyone. Thanks for your time. Yep, that's it. Thank you.